Section 1.7 is titled Modeling with Functions. Mathematical modeling is essentially using mathematics to model or represent real-world problems. Essentially, this is the some of the material that gets into the why do we do mathematics, what's its purpose. I'm going to give you a variety of different examples from the text that show some things that we can do with the mathematics that we've been learning so far. So these are real-world problems. These are story problems, if you prefer, word problems, if you like to call them that, modeled mathematically, solved mathematically. First example says, on their 560-mile trip, the Bruins basketball team spent 2 more hours on the interstate highway than they did on the local highways. They averaged 45 miles per hour on local highways, 55 miles per hour on interstate highways. How many hours did they spend driving on local highways? Okay, so I see quantities in this problem like distance. I see speeds, which are rates. And I want to answer the question, how long, which is time. So there is a distance formula relationship. Distance equals rate times time. If you know how fast you're going for how long you're going that speed, then multiplying the rate and the time together tells you how far you will travel. Okay, so I'm thinking, just based on the numbers and the quantities I have in the problem, I'm thinking this is going to be a mathematical model that I can use. Now I'm also going to set up maybe a picture to help me visually see this problem. So I've got a 560 mile trip, and I spend some of that time on local highways, some of it on the interstate. Okay, so what do we know about the time spent on each of those respective types of highways? Well, we know that on the local highways we had a rate of 45 miles per hour, and on the interstate we averaged a rate of 55 miles per hour. Now on the local highway, what about time? We don't know that. We want to know how many hours did they spend on the local highway. So I don't know how long. Let's just call that X. Now what about how long I spent on the interstate? Well, I don't know that either, but I do know that I spent 2 more hours on the interstate than on the local highways. So if I spent X hours on the local highways, then the interstate was X plus 2. Okay, so I can find this distance by taking r times t. I can find this distance by taking r times t. Since I know that the sum of their respective distances is 560, that's exactly what I'm going to do, is find their sum. Okay, so I get the following equation. I get 45x plus 55 times x plus 2 equals a total distance 560 miles. Let's solve this equation. 45x plus 55x plus 110 is 560. I'm going to take this 110 over and I'm going to add these x's, so I get 100x equals 450. If I divide by 100, we get 4.5. X is time spent on local highways. That's what I'm trying to solve for. Units are going to be in hours. So I spent 4.5 hours on the local highways. This problem says Ruth is weighing 2 job offers from sales departments of 2 competing companies. One offers a base salary of $25,000 plus 5% of your sales. The other offers a base salary of $20,000 plus 7% of her sales. What would Ruth's gross salary totals need to be to make the second job more attractive than the first? And so obviously if she chooses the second job, she gets paid less money up front, but she makes a higher percentage of what she sells. So if she is really, really good at selling, then that's probably the better offer. But the question is, how good would she have to be? Okay, so let's just kind of set them up. Job 1 is going to pay her $25,000 plus 5% of what she sells. We don't know what she sells, so let's call it X. Job 2 is going to pay her $20,000 plus 7% of what she sells. Okay, so what would her sales have to be to make the second job offer more attractive than the first? We want this job to yield more money than this job. So let's set job 2 greater than job 1. And let's solve this inequality. To do that, I'm going to subtract 0.05x to this side. I'm going to subtract 20,000. Okay, so I now have 5,000 less than 0.02x, and I finish that by dividing both sides by 0.02. If I divide both sides by 0.02, $5,000 divided by 0.02 is 250,000. So her sales X would have to be greater than 250,000. If she could sell more than 250,000, she would want to choose the second job. If she doesn't think she can sell more than that, she should choose the first job, because then she'd make more money as she's getting more up front. This problem says that from 1996 to 1997, the U.S. shipments of personal computers grew from 26,650,000 to 30,989,000. What was the percentage increase in U.S. personal computer shipments? Well, the percent change, there's a way to compute that, is found by figuring the amount of change divided by the original amount. Okay, so let's do that. The amount of change would be found by finding the difference. Okay, the difference between 30,989,000 and 26,650,000. So I need to subtract these two quantities. If I subtract those two quantities, we get 4,339,000. I want to divide that by the original amount, 26,650,000. If I divide that, we get 0.16, let's just go 28. So the percentage increase was 16.28%. This next example is an example of what we commonly call a mixture problem. It says the chemistry lab at the University of Hardwoods keeps two acid solutions on hand. One is 20% acid, the other is 35% acid. How much 20% solution and how much 35% solution should be used to prepare 25 liters of a 26% solution? So generally in this type of problem you have a smaller percentage solution and a larger percentage solution. You're trying to mix them together to get some percentage that's in the middle, 26 being in the middle of 20 and 35. Well, not directly in the middle, but it's between the two. Okay, so I kind of set it up this way. I've got my two solutions. One of them is 20%. The other is 35%. I want 26%. Okay, so that's my percentages. Okay, and maybe you can think like this. I'm adding these together to get this. Okay, I'm combining these two together to make that one. Okay, well, what I need to know is how much of each. Okay, how much of each do I need? Well, what do I know? I know that I want 25 liters in the end. Okay, so I have to divide up 25 somehow. You know, is it 1 liter and 24 liters? Is it 2 liters and 23 liters? Is it 12 and a half and 12 and a half? You know, I just don't know. So since I don't know, let's put X amount there, and let's put the remainder over here. If I need 25 and I put X of it here, then the expression 25 minus X would show how much is going to be left over here on this one. Okay? Or think of it this way, X plus 25 minus X is 25. So it works out that way too. Now the way that I set up my equation is I do the percentage times the amount. Okay, so the percentage would be 0.2, 20% is 0.2 times the amount, plus, I need the percentage here, 0.35 times the amount, equal to the percentage times the amount. Percentage times amount on all of these different concentrations or solutions. Okay, so on the second term, the 0.35, we are going to distribute that, 0.35 times 25, so let's see, I've got 0.2x plus 8.75 minus 0.35x equals, I'll go ahead and multiply these together, that's 6.5. I'm going to combine my like terms. So 0.2x minus 0.35x is negative 0.15x. Subtract my 8.75 across. So 6.5 minus 8.75 is negative 2.25. I'll divide by the negative 0.15. And I get x equals 15. X belongs here. So that tells me that I want, change colors here, that tells me that I want 15 liters of the 20%. And if this is 15, then 25 minus 15 tells me I want 10 liters of the 35%. So if I mix those two solutions together with those quantities, I will have the 25 liters of 26% solution.